Excellent. Okay, how to build a muon telescope. So this is based mostly on the work, like Sid said, that I did over the summer here at Exeter, and where I built, or at least attempted to build, a muon telescope. A more accurate name for the talk might be How I Learned to Stop Worrying and Love the Muons. And we'll get more into that later. But I've been told to sort of pitch this talk to the level of the sort of general public. I'm going to give you all a little bit more credit and assume that because you've come to such a brilliant conference, you're naturally more intelligent. But we will be starting at the beginning with what is a muon. At this point, I've threatened my friends to stand here for 20 minutes and wait for an answer, but I won't do that. And they say a picture paints 1,000 words, so there you are. But I think I might have to use some words as well. Well, a muon is essentially an exotic particle. And what do I mean by that? Well, we have our normal particles, which are the protons, neutrons, electrons, everything that makes up me, you, the table, the screen, all of that stuff. And then, you have everything that's not a normal particle is an exotic particle. Like, muons and tauons and muon neutrinos, tauon neutrinos, photons, but there are so many of them. They go on and on and on, and then, you have all the quarks and the mesons, and then after that, you have the quasi-particles. So yeah, no, this isn't a good way of categorizing things, but it's how physics does it. So, well, we're going to look at it in terms of a comparison, right? We'll compare to probably the most well-known exotic particle, the neutrino, right? There are 3 interesting facts that people will tell you about neutrino. Number 1, it's nearly massless. So very nearly massless that for the longest time people thought it probably is massless. Turns out it isn't, but it's very close. Number 2 is that there are 3 flavors of neutrino. So you've got a lot of options there. And number 3 is the sort of most amazing one. This is that there are hundreds of trillions of neutrinos traveling through you every second, which is incredible. So how do our muons stack up? Well, instead of being nearly massless, a muon is actually sort of in between the mass of an electron and a proton, which isn't very impressive. It's right in the boring region. Instead of 3 flavors, we have just the one. And instead of hundreds of trillions of neutrinos, we've got tens of muons, whole tens, traveling through you every second. Now, okay, at this point, you might fairly be saying, why do you care, right? Why on earth do I care? Borefest, right? I'm going to change your mind about muons in 2 words, hopefully. Ready? Secret tunnel. Words that invoke mystery and wonder, right? What do I mean by this? Well, muons are generated in the atmosphere. And because of that, the flux, which basically means, so if I were to hold my hand up like this, the number of muons that are going through this area is the same, no matter if I point at that part of the sky or that part of the sky. Because of that, it means that the only thing that changes how many muons I'm going to count with my detector is what's in front of my detector. So essentially, if I put a big slab of lead on top of my detector, I'm going to have a hard time seeing a lot of muons. And in the same vein, if there's a pyramid in front of your detector, you're going to have a hard time seeing a lot of muons. But you know how big the pyramid is. And if the pyramid is a certain width, and your muon detector is saying it's a different width, well then, you know that there's a secret tunnel inside the pyramid. And I'm not just making this up. This has actually been done, and muon detectors have been used to look at pyramids and find hidden passages. And the other thing you can do with them is you can look at the internal structures of buildings, and you can come up with these sorts of photographs here, where you see the internal structure of buildings, where this is actually the core of the Fukushima nuclear reactor, something you wouldn't be able to take a normal photo of. So hopefully now I've sold you on why they're interesting. Now the question is, how do you build one? And basically, a muon telescope is pretty much just like a camera. And I'm going to break it down into 3 sections. We have the sensor, the electronics, and the data reading, right? So first, we'll talk about the sensor. This is essentially a big piece of plastic. It's specially treated plastic. We call it scintillator. And what it does is that when a muon hits it, it will glow very, 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 very slightly. So slightly, I mean, you wouldn't be able to see it. Not with, a normal light. I mean, that'll ruin it completely. So, these things have to be, wrapped in tinfoil and then covered in duct tape and then put in a metal box, and then the metal box needs to be screwed down and then put in a dark room, and then you're okay. Because we put a little detector that can detect light on the edge of this scintillator plate. And therefore, when this gets hit by a muon, we get a small signal, which is fantastic. We now have a pixel. Now, sort of for comparison's sake, my phone here, it has like a 12 megapixel camera or something. I don't really know. We've got 1 pixel, which is less than ideal. So how do we get more? Well, we can split our plate into separate sections. That way we know if we're getting a signal from one section that that's where the muon is coming from. Brilliant. Of course, you'll realize this is going to complicate things because we need electronics for each of those sections. And that, you can see, will very clearly complicate things. Here we're only dealing with 16 pixels. And already, things are getting messy. Well, I've been talking about these electronics, and, I just want to give you a sort of an idea of what we're working with. I mean, right here, this is, actually one of the larger pieces of electronics that I used over the summer. It's called a Schottky diode. And, we're literally talking about grabbing these sort of things, the sort of things that just you see on circuit boards, soldering them together, and coming up with a system that'll work to allow you to detect muons. And just sort of as a side note, if you ever do get the chance to order electronics online, it's fantastic. Because if you love getting deals, you'll love getting electronics. Because, you see things like 500 diodes for £1, or 1,000 diodes for £1. It's fantastic. Anyway, sorry, I've sort of gone a bit off topic here. So out of the sensor, we get a small signal. And purely from the sensor, we just get something that looks like this. Very small, very short in time, not very useful. So our electronics are going to be dealing with that. So first thing we do is we put it through a transimpedance amplifier, which is a fancy way of saying an amplifier. And what that does is it improves the magnitude of the signal. That way it's much clearer to see. But we can do better than that. We can put it through a Schmitt trigger. And what the Schmitt trigger is going to do is it's going to digitize the signal. So much like a computer only deals in ones and zeros, the Schmitt trigger is going to say, okay, beyond a certain level, I'm going to set the signal to equal 1, and below that level, I'm going to set the signal to equal 0. That gives us a really clean, really clear square wave. So it's very obvious when you have a muon and when you don't. So why is that important? Well, it's important when it comes to the data reading. Well, now, you might be tempted when you're sort of designing this sort of stuff to use one of these for data reading. It's a small off-brand Arduino Nano, a sort of fantastic little microcomputer. You can program things online, write them, put them on here, and have it do all sorts of wonderful tasks for you. And this is a fantastic idea. They're very cheap, fantastic for hobbyists, and they can actually take a measurement around every millionth of a second, right? Unfortunately, our signal lasts about a billionth of a second. Now, you can appreciate that if you're only taking a measurement every millionth of a second, and the signal only lasts 1/1000th, chances are you're going to miss the interesting thing every single time. You'll take a measurement here, and then the signal will happen, and then over here you'll take a measurement, and nothing will be happening. So that's why the transimpedance amplifier is so important, because not only does it amplify the signal, but it stretches it out as well. Now, instead of just seeing nothing, we're actually seeing a signal. And then the Schmitt trigger just does that extra bit of making it brilliantly, perfectly clear. Fantastic. Perfect. So now we've covered the 3 bases. We know what we need to do, and we can build this, right? What could possibly go wrong? Well, I'll tell you from my work over the summer that there are 3 major areas for errors in this project. There's the sensor, the electronics, and the data reading. As well as some smaller areas which include all of the connections between those points. But you internalize this, you accept this, you power on, and you plug it all in, you put it all together, and you manage to build something, you connect it to your oscilloscope, and then at last, you have muons, right? Brilliant, fantastic. Wrong! These aren't muons at all. What this is detecting is me. Which is rubbish because I know where I am. So, the problem with working with an amplifier, a transimpedance amplifier, is it will amplify everything, including the small electrical signals on my skin, including the power bank that I turn on halfway across the room that's not connected to anything. I mean, this is sort of what I want to get to with the crux of my talk. If you forget everything, but only take one thing away, this is what it is. And this is sort of a love letter to SpaceX as a whole as well. Because you will be astounded by the creativity and the magnitude of ways in which you will be wrong when you do all of this. It is incredible. And the reason I want you to take this away is because, this is the 21st century now, right? You could all go away and look up muons and read papers, read the papers I read and watch videos that I watched and learn how to build a muon telescope, right? It's all available out there. But when you're building anything, be that a muon telescope or the XRTC or the HAB or programming anything or doing any sort of project, you're going to break things. You're going to break hundreds of pounds worth of things. And and at some point, you will realize that this device that you're measuring the muons on is worth many multiples of what you're getting paid for the whole project. And you've got to realize that, and you've got to internalize that, so you can, learn from your mistakes, because it'll never be enough to get things right the first time. Because if you do, you'll get them wrong the second time. What's important is getting things right the 10th time, the 20th time, the 30th time, the 100th, the 1000th time. So now just a brief story from when I was working on this. I'd been working on a problem since for the whole week. So I'd only just solved it by the end of Thursday. And I came in on Friday and I was thinking, absolutely brilliant. Finally got that problem sorted. I started chatting with one of the other researchers and he was telling me, oh, the department is in quite high spirits today. And I said, oh, why is that? He said, well, we managed to solve a problem that we've been working on for 10 years. I thought, oh God, what was that? What was this problem? He said, well, in the simulations we've been running, there have been a few sort of structural elements, and we've been, for 10 years, we've been looking at them and trying to explain them and understand them, making posters, going to conferences, trying to convince people that these things exist and they're real. About a week ago, we had a visitor, and he suggested we make a few changes to our code to improve it, and we did, and all of those structures went away. So the problem that they solved that lasted 10 years turned out to just be an error. And I mean, that might sound terrible, but it's actually fantastic. Because it's much more important to know that you're wrong than to think that you might maybe be right. Because there's certainty in that. And that allows you to move on and learn from your mistakes. So that's what happened with the Muon telescope. By the end of the summer, I hadn't quite finished the project. It was in a good place, but you have to stop somewhere. And from there, it has been taken over by a group of natural scientists in their third year. They managed to do a lot of work with the project, and it's in a really good place now. It works really well. And hopefully, it'll just continue to develop again in the future. And I think that's the most important thing to learn from doing science, is that you got to learn from all of this, much like they learned from my mistakes. And if you're going to build a muon telescope, you're going to make a mistake. All right. Thank you. Ooh, I pressed the button I'm not supposed to press, Sam. There we go. Any questions?